Zoom recording. Okay, we got blinky red light. Good sign. Okay, so you guys all seeing the schedule up on the screen? No? You're not. Okay. Then stop sharing. Let's try this again. Share screen. That. Glad I asked, or else I'd just start talking. Okay, I see a thumbs up, so now we're seeing it. Okay, I decided that today we can cover both electrical and interior lighting. So for Friday, I'm going to make it an optional class day where you guys can, I'll be here online. You guys can click in and ask me any questions about assignments. There might be assignments about the PV layout assignments or any of the past ones, or just questions. I'm just going to make it sort of like an open house day. Normally, if we were like in a classroom, I would often, have, meetings or checking in with students. They needed anything. It's this whole virtual thing's a whole new world for me. And you guys don't ask that many questions, so we're rocking through all the material here. So we're going to get through both electrical and lighting today. And so Friday will be optional. I'll be here. If you have questions or want to talk about anything at all, everything's open. So just let me know. And I have updated the schedule on Moodle also. So this one that you're looking at on the screen is the most recent one too. So, any questions before I jump into the lecture? It's very exciting.
No questions.
Thank you. Actual voice, I like that. Okay, electricity, and then we're gonna go into lighting, which is artificial lighting, because we've already covered daylighting. Electricity. So a couple of things to think about electricity. You can, there's a good way to think about it. Water is a good analogy for thinking about electricity. So if you think about water and how it flows through a pipe or a hose, electricity is very similar in terms of flowing through a wire. So the wire is the same thing as a pipe or the hose. And then the electrons that are the electricity part of it are flowing through that wire. We don't need to get into the chemical aspects of how the electrons are transferred from one atom to the other, but if you think about it on a similar level to water, I find that really helps understand some of the concepts. But the terminology is a little bit different. Okay. Oops. Just trying to keep track of people as they come in. So there's several terms about electricity that are essential for understanding. The current, which is measured in amps, is the flow of the water. So that's the volume that is moving through the wire. So it's the current, and it's for the formulas, it's expressed as a letter I. I have no idea why, but it's measured in amps or amperes, and that's where the electrons are moving down the tube, which is the wire. So that's the current. The second concept is voltage, and this is the force. This is the power behind pushing the current, the amps, down the tube, which is the wire. Okay, so the stronger it is, the faster the current is flowing. And the force, which is the voltage, is measured in volts. Pretty straightforward. We've come across the concept of volts before. I'm going to tie this a little bit into some PV concepts we went over last week. Current is the flow, voltage is the force, and then very similar to when we were looking at heat conductance through a material, there's also going to be resistance, and that is measured in ohms, and that's very similar to like the insulation value in a material. That's what's preventing or hindering the flow of the amps down the wire. So the volts, which is the power, is equal to the current, which is the flow, times the resistance. The resistance is impeding that flow of the electrons. So similar to a heating load or a cooling load on a building, we talked about BTUs, which is a measurement of energy. This corresponding concept in electricity is the power, which is the kW, or the kilowatts, or the watts, okay? It's like BTUs, it's an instantaneous measurement of power. It's not, it's just instantaneous. So when we're looking at PV systems, we looked at modules and module cut sheets and how a module is rated for a certain number of watts, like 300 watts or 350 watts. That's the theoretical maximum of the absolute amount of power that that PV module could produce at an instantaneous moment under 100% ideal conditions. Okay, so power in terms of electricity is it's just that instantaneous measurement. But energy, which is like the load, the heating or the cooling load, which is BTUs per hour, in electricity, it's kilowatts per hour. So it's over a period of time. You have to have that time factor in there, and then the power factor. So it's like the flow rate. Okay, so a building load is the amount of energy over a period of time that's required to change the heating or the cooling level of a space. For electricity, energy, which is your consumption, this is like how much you're going to use over a period of time, is your kilowatts per hour. So when we were looking at our PV system layouts, the modules had the watts, which was a measurement, that instantaneous measurement of power that it's theoretically possible. But then you, through looking at using the PV watts calculator, which was importing the data on how much sun radiation was hitting an area over a period of time, that was giving a production rate for that PV system. That's the energy. And that directly corresponds to the energy that you're going to consume in a building over a period of time. So cooling and heating loads were BTUs per hour. That's how much over a period of time you needed that amount of energy to heat or cool the space, just to change the temperature. With power, it's the same, or with electricity, it's the same thing. Over a period of time, you're building your space, your room is going to consume a certain amount of energy over a period of time. So when you look at an electrical bill from SDG&E, we get billed, or LA Power and Water, we get billed per kilowatt hour because that's the actual consumption of how much we are using. And in order to quantify that, that's where the time frame comes in. It's because it's not just a single point in time. It's over a period of time. And similar to how we were talking about bear with me 1 second. Similar to how we were talking about time of use billing rates with our utility companies, how right now in California, electricity is being billed to us at a different rate based on the time of day, based on when we're using it. And there's all these factors that are coming into affect that. That's, you know, all the solar powers, all the solar panel systems that are putting energy into the grid, when people are using it, when they're drawing it out. We looked at the duck curve last week or the week before. So currently, not to play on current, which is the flow, in California, our energy has a different monetary value based on what hour of the day it is. And so if you can remember that, thinking about energy, that could, I would hope that would help you remember that energy needs to be thought of over a period of time. And our period of time, our default value of measurement is going to be the hour. So kilowatts per hour. And it's the same thing. My beef with BTUs per hour, kilowatts per hour, they don't actually put the slash in the units, which drives me crazy. But it is what it is. Okay. So we talked about current, voltage, resistance, and then we were talking about power. So let's see how these all come together. So our power is our watts. In order to calculate what our watts are, that's going to be based on the volts times the amps. So that's the current, let's go back here, the current times the voltage. So your amps times your voltage will equal your watts. So that's your instantaneous point of measurement of a total amount of theoretical possible electricity. Okay. Your volts is going to be based on your flow rate times your resistance. So that's your flow is your water that's going through the pipe, and your resistance is the material that electron transfer is occurring through as it's going through that pipe, the pipe being the wire. So our power, if we back it up, is going to be volts times amps, and then our volts is going to be the amps times the resistance. So our power is going to be all three of these, which is your volts times your, volts equals amps times resistance. So that's your amps is your current. Your power is the current times the resistance. And so the watts is going to be your amps times resistance times amps to get your watts. So therefore it's with the symbol letters, IR, which is volts times current, times your amps again, you're going to get your I squared R. So it's your amps squared times the resistance. Or if you want to calculate for, you can reverse that to the volts, which is your, I'm just trying to keep my terminology straight here. Your volts is your force, or your force squared divided by the resistance. So it's either amps squared times resistance or force squared divided by resistance. Okay, yeah, that's a bunch of letters, a little bit of a formula. How do I remember that? What does that mean? So let's put it into the context of a real world example. Your 60 watt incandescent light bulb, 60 watts, okay? So watts is the power. That's the theoretical maximum number of watts that that light bulb can shine at a given instant. So at 120 volts, which is our standard electrical distribution system for line voltage here in the United States, you only need 0.5 amps, which is the current, to run that light bulb to give off 60 watts. If we were to step that down and do that, look at that in what's a low voltage system, and we'll talk a little bit more about low voltage versus line voltage in a minute. If you only have 12 volts of power, so your power is less, you're going to need more current flow to equal 60 watts. So therefore, you're going to need the 5 amps to equal that 60 watts, because your flow rate is, or your power, excuse me, your amps is your flow, your watts is your power. To get that same power at a lower voltage because of the resistance, you're going to need more flow, which is the amps, to get that same equivalent amount of light out of that light bulb. Okay. It's a lot of information in just a couple of slides. Let's take this to the next step. Skip the next slide real quick. And let's go back to talk about current again.
I like the title.
Okay, so my husband saw this slide and he's like, are they gonna know what AC/DC is?
Yeah, come on.
And I'm like, of course they are, hello. But hey, anything to get your attention, because I know this is, the electricity part's a little dry. The lighting's gonna be a little bit more interesting. Okay, so current, that's our flow rate. So there's 2 methods of current, and they're used in 2 different systems. Our main electrical distribution system in the United States is alternating current. And that's what, if you have an electrical outlet on the wall, it's 120 volts, it's going to be AC current. You're going to plug in a plug for an electrical appliance into that. And that's the main distribution system. So alternating current is where the voltage is consistently flip-flopping, kind of like positive and negative, but it's a positive and negative sine wave because electricity is just another flow. We'll go with that. Current, it's a flow. It's like water going through a pipe, okay?
Was DC versus AC the battle between Nikola and Edison?
Yes, it is.
Right. Okay.
Was. I'm going to talk about that in just a second. So the frequency of that alternation is measured in hertz. Our system happens to be 60 hertz. I believe Europe runs more on 50 hertz, but it's not really going to affect you particularly much unless you start doing a lot of international work. And then you're going to work with an electrical engineer who's going to help you all out with it. But just so you're familiar what the hertz is, it's that frequency of how fast that current is flip-flopping from the positive to the negative. Okay, so that's alternating current. Direct current is straight, just constant flow in one direction without stopping to be positive or negative. Okay, and as David just mentioned, when electrical systems were first started putting into use in the 1880s, there were three major powerhouses, or three really smart guys. There was Thomas Edison, famous for the light bulb. There was Nikola Tesla, which is now back in popular current thought because of the Tesla car company.
He's part of the zeitgeist right now.
Yes, that's a good way of putting it. And then there was Westinghouse, and I forget what his first name was. So Edison favored alternating current because that's what he came up with first when he was first inventing the light bulb. Nikola Tesla actually worked for Edison as a young intern, but he came up with the concept of, excuse me, I just said that wrong. Edison was direct current because direct current flowing through the light bulb. Nikola Tesla, when he was working under Edison, came up with the concept of the alternating current, which travels better. It's better for a distribution system. And so this was called the War of the Current, or War of the Current. And they were both taking out patents, and they were both trying to get commissions to install systems in different cities. Before the United States was all connected together in this one big electrical grid, it was city by city or municipality by municipality. Each little one was putting in their own distribution system. And I don't know when they all started coming together, but so there's this big battle going on of which was better. And Tesla ended up selling his patents for alternating current to Westinghouse, and Westinghouse was able to sell systems and install them and made a shitload of money. Excuse my language, made a lot of money. And Nikola Tesla died in poverty. But the reason alternating current is a better system for long range distribution is it can travel farther distances without losing as much force, as many volts. Direct current works really well, but over much shorter distances.
Nikola Tesla was the first to theorize that we could have wireless electricity, basically, right?
I do not know.
That isn't that kind of why they started shutting him down a little bit?
I don't know that. I know that from what I've read, he was the proponent and developed the patents for the AC system.
Right.
I really don't know anything about wireless. But you've spiked my interest and I might go look it up now. Today, we have pretty much two different systems that are working pretty much in harmony together. For our large distribution of power traveling from one location to the other, we use alternating current. But on a much smaller scale, we use a lot more direct current systems, especially with the influx of solar electricity, because a solar module is it's the silicon and it's production of electrons, and it produces energy in direct current. As the solar radiation hits the silicon in the cells, the electrons are transferred into the wires in the module, and they all collect together, and that's all in direct current. So in a solar system, solar electric PV system, all that electricity is collected together and it goes into either a battery for storage, which is in DC, which is direct current, or it has to go to an inverter, which transforms it into alternating current to feed into our electrical grid. So when you guys are doing your PV layouts and utilizing PV watts, the second page where all the input was, there was the power loss button that I said, don't really worry about. It's set at like 14.08 or something like that. That's the loss that occurs in the inverter when you're converting your direct current produced by your solar module into alternating current through your transformer in order to backfeed it into the grid system. But you could just store it straight up in a battery before it even reaches the grid. And we talked a little bit about how battery storage is going to be more and more prevalent. And there's a lot of questions on, well, there's different thoughts, and that's one reason why the battery technology is changing so much right now, is do you store your energy in DC, and then if it doesn't fit in your battery storage because you're maxed out, you run it through the inverter and put it in the grid? Or do you want to convert it to AC and put it in the grid and then feed a battery off of the grid? Anyway, there's a couple of different ways to do it. There's options right now, and technology is still adjusting and moving forward. And just a point of interest is if you're talking to a electrical engineer that works a lot more in the solar or the battery industry, they call it power electronics is the industry word to describe the inverter transformer technology that is the hub between your DC and your AC system. That's all the power electronics. And so this is like that, it's that nexus of where these two different systems come together, and you have to, and this gets way into more electrical engineering than I comprehend, matching all of these different voltage, amps, power, everything coming together is the limiting factor. That technology is a limiting factor right now. And so when the Tesla Powerwall was first coming on board, which was advertised like 15 years ago, and now you're just finally able to start installing them, they were having a real struggle with their power electronics. I heard this from a solar rep. Actually, no, a battery rep for a battery company, that they really struggled to get that inverter battery storage part of the technology that made it seamless to take your PV system, plug it into a battery, take your grid system off your electrical meter, plug it in the other side of the battery, and have that power wall do all those magical things and just make everything work. but now you can, I think they've worked out a lot of that, and I've seen more and more of the Powerwall battery systems installed. Okay, so that's current. And let's see, I'm gonna jump back to, actually I'm gonna go right straight to here. Actually, no, before I do that, just a few more pieces of terminology that you guys are gonna run into during your careers. The National Electric Code, NEC, that's an abbreviation you're gonna see a lot. And then almost even more than that, you're gonna see NEMA, National Electrical Manufacturers Association. And there's gonna be certain things that are gonna be like, is it NEMA rated? Is this NEMA outdoor listed, indoor listed? They do a lot of setting standards for the performance level of equipment that you have to buy. Okay, so you're gonna see that. And you're also gonna see the term UL, Underwriters Laboratory, which is a giant corporation, but what they have done is established a testing procedure to meet all of the various different testing guidelines by different industries to verify that certain products meet the guidelines of the testing regulations. I have my personal opinions on it, and I kind of think of it as like a giant mafia, because it's one of the main rating systems that a product has to be tested through in order for municipalities that are enforcing building codes to approve your products or your building. However, it's a private company, hence mafia. Kind of big racket in my mind, but at least it does provide a level of safety and a level of guarantee that products meet a level of performance. For example, I think I mentioned, I was talking about cut sheets the other day, and that I had to find a cut sheet for a gas fire pit for a project I'm working on. The building department insisted upon having a UL listing number for the gas fire pit. And major pain in the ass, because gas fire pits, apparently they're all manufactured in Canada, and so they all have Canadian rating listing on them, which is CA, Canadian whatever. Took me forever to find one that's actually UL listed. Anyway, you're going to come up against this. So I thought I would bring it up and let you know what you're going to be seeing down the road. Okay, we talked about AC and DC. And the last thing or concept, well, more info, I wanted to go over is the phases of power. And this is something that you'll eventually probably run into. There's, within our grid system and our utility company providing power to all of our various locations, believe it or not, there's two different ways that they do it. There's single phase AC, and then there's three-phase AC. And what you will find is that residential neighborhoods, residential areas will only have single phase power in the distribution lines that you can access, versus commercial areas will typically have three-phase. Sometimes you run into a location that it doesn't, but there, and what it has to do with is different equipment is rated at different phases and how many basically how many wires you have to wire into it. And residential equipment is designed to be single phase. And what the effect of that is that the size of most mechanical HVAC units that go onto a residential project are designed to be single phase, and they will max out at about a 5-ton capacity. Because if you think about it, majority of residences are 2,000-3,000 square feet max, or a lot smaller. They're not giant buildings. The heating and cooling loads are a lot smaller. Therefore, a 5-ton unit is a reasonable size. However, once you start getting into much larger buildings and you want to have much larger equipment, you're going to want to put in, instead of putting in 4 5-ton units, you're going to want to put in 1 20-ton unit, because then you're only buying 1 piece of equipment, and that's going to be a lot more economical than 4 pieces of equipment, and usually less square footage, which is going to keep your footprint size down, which is going to keep your overall building cost size down. So just be aware that there is a difference and from residential to commercial. Now, as architects, there's a high possibility that at some point you're going to be working on a very high-end residential project. I shouldn't say high possibility. There's a possibility. It really depends on the direction you want to take your career. A lot of architects end up doing a lot of high-end residential, where you're talking about a 20,000 square foot house, which starts getting into the commercial scale of buildings with much larger heating and cooling loads, but you're stuck with residential sized equipment, and many residential areas don't have access to 3-phase power. So I just bring this up because it could potentially be on a project that you've come across somewhere down the road. So my synopsis on how does this affect you? Not a whole lot, but I want you to know about it. I want you to know the difference, and being aware that single phase HVAC equipment, we haven't talked about active equipment in a while, but the power needed for that equipment, or the power available for that equipment size, equipment maxes out about 5 tons. And it has to do with all those previous terms we were just going over about power and flow and amps and resistance. So at the end of the day, residential projects are typically single phase, commercial projects are typically 3-phase, and they have different specifications for equipment. This might also come up when you're working with your mechanical engineers and you are looking to approve submittals on equipment during construction administration. So being an architect who is aware of these nuances within the engineering side of the field will take you farther in working with your engineers in impressing them with your knowledge base. Okay, last thing about straight up electricity is to throw in the sustainability aspect and or looking at your total building loads and where your usage is going to go. These charts are within the last 10 years. They're fairly accurate now. Lighting loads, if anything, are going down a little bit because of the LED technology progressing farther forward. which really makes a huge dent in the power or electricity needed for your lighting load. But I like these two charts because they break out space heating from space cooling. A lot of electrical breakdown loads just say like building conditioning, 33% of your load or 45% of your load. I like to see it broken down between heating and cooling. And it differs a fair amount between commercial and residential. That space heating's about the same, 25, 27%. Cooling is 9%, 11%. So it's a little bit bigger on residential. The loads are a bigger chunk of your electrical pie. Water heating is much bigger on residential because commercial use, you're not taking showers, you're not, well, it depends on the commercial use. It's not as great. Refrigerators, freezers, cooking, office equipment. The only thing you can really make a difference with in your designs and working with your engineers is the other load. And that's, if you're trying to get like a super efficient project, that's where you can target trying to keep those loads down. That, and then also lighting. Really coming up with a highly efficient lighting design can make a big difference. Although in California these days, our Title 24 performance requirements are super tight to begin with. So it's harder and harder to make, to be performing above code by a significant amount. Okay, so going off of lighting, jumping into the second half today about interior lighting design. Before I go there, does anyone have any questions? Oh, okie dokie. So, a lot less equations on the lighting side, and more inspirational images. People are attracted towards light. Just like plants, we're kind of like giant plants. Light attracts our attention, we're drawn towards it, it creates an interest. We don't necessarily grow and bend towards it like plants do, but there is that attraction. And we can use that attraction in lighting designs to enhance our buildings and how to use it to control people from moving through a space. Phototropism is the official word for why we are attracted towards light. Also ties into our circadian rhythm and our body's response to natural light and knowing what time of day it is. I know my dog has the hardest time at daylight savings time because she always wants to eat either an hour early or an hour later and cannot understand why we're not feeding her because the light levels haven't changed in her opinion versus all of a sudden it changes from 4 to 5 o'clock and she thinks she needs dinner earlier than she should just because we live by a political clock. Okay. The most primary concept in artificial lighting is direct versus indirect. And there are fixtures that do one or the other, and then there's a whole slew of fixtures in the middle that can do both. Direct is where the fixture is straight and goes out. The light comes out from the fixture and hits a surface. Indirect fixtures rely on another surface for their lighting effect. And that other surface can be thought of as an extension of that fixture. If you have indirect lighting that's shining off of a white ceiling, you're going to get one effect versus indirect lighting that's shining off of a black ceiling or a very dark color. It's not going, the fixture relies on those surfaces for that distribution of the light. And so you have to keep in mind that extension of that light fixture and how that's going to affect your lighting design. So, whole bunch of different options for types of fixtures. So for some direct fixtures, we've got a wall sconce, a recessed can light, a recessed fluorescent light, task lighting, a direct pendant. Many pendant fixtures, though, you'll find can be both direct and indirect. Then for indirect fixtures, there's wall washers, under cabinet lights, a recessed cove light, indirect component of a pendant fixture. All of those indirect fixtures are going to rely on those surfaces around them to help distribute their light to meet their design goal. A little bit of terminology that you should be familiar with and understand, so that either when you're looking at a lighting fixture cut sheet or you're working with a lighting designer and they're sending you cut sheets to look at and review, that besides just the aesthetics of how that fixture looks, you can look at the data and see, oh, this is a really powerful light, or oh, this light's not doing very much, or oh, this is a really bad quality of color rendering, which we'll get to all of these. Okay, so spread is the angle. It's the angle of the light that the fixture is giving out. And a lot of fixtures have options on angles and or the type of bulb that you specify with the fixture can also have different angles for spread. When you're talking about lighting, the lamp is what your light bulb is. The lumen is the amount of light. That's like the volume of light that you're getting. And that's measured in foot candles. And that's based on 1 lumen per square foot equals 1 foot candle. Candela is the intensity of the light. So that's kind of like the power. So lumens would be the flow-ish, and candela would be the power behind it, the how bright it is. Because you can have a very small bulb that's really bright, and so it has a lot of intensity, or you can have a very big bulb that's not very bright, but have the same number of lumens, but it's spread over a larger area. So the intensity would be a lot less. And that starts to get into how far your fixture or your bulb can throw the light. So when you're looking at a lighting design, and we'll get there in a few more slides, is looking at how far that light fixture is going to illuminate a surface with what level of lumens, 5 feet from the fixture, 10 feet from the fixture. This makes a big difference if you're looking at pendant lights or recessed pendant or recessed fixtures. Typically, like task lights, you're only talking about your throw light being a couple of feet. Wall sconces are usually, you know, just affecting the area around them, but pendant lights can be trying to illuminate a large area over a table or in a classroom. Visible spectrum, that is the visible light that the human eye actually sees. And there's a light temperature, which is measured in Kelvin. And then the CRI, which is the color rendering index. And between the temperature and the CRI is what what make up the quality of the light. Temperature is simulating daylight temperatures, and there's a range. And then CRI is the quality of the colors that you can see for that lamp and or fixture. So 1 foot candle. Guess why it's called foot candle? Somebody at some point in time decided, okay, how much light comes off of 1 candle over 1 square foot at 1 foot away. Now, assuming all candles are made equal, of course. At this point in time, it's just measurement of quantity of lighting on a surface. But keep in mind that your foot candles or your lumens is that measurement at the surface. It's not what comes off the light, it's where it's hitting a surface. Because if you think back to the first slide, your light's either direct or indirect. So if you have a direct light, that light's coming down and shining on a surface. That's where you're measuring the lumens. If you have an indirect fixture, that light is bouncing off of 1 or more surfaces before it hits the final surface, and that's where you measure the lumens. So sometimes, depending on your goal, your indirect fixtures might need to have be more production out of them so that by the time the light hits the final surface, it's at the lighting level that you're looking for. Or you need a brighter bulb. Candela is the, let me see here, the intensity. So it's, again, a smaller bulb could have the same output as a larger bulb, but in a smaller footprint, it's a higher intensity. So the lumens are the amount of light that hits the surface. The candelas are at the bulb or the lamp for the fixture. And the two of them work together to determine what between the candelas coming out of the fixture and the bulb or the lamp, and it's going to help determine what the lumens are going to be on your final surface. Candela is probably the hardest concept to understand about interior lighting. So our lumens are on the surface. The intensity is the candelas that are coming out of the lamp. Well, this maybe isn't the best diagram. Because it's, okay, so the illuminance is over a period of area of how many lumens per square foot, which is your foot candles. Flux, I wouldn't worry about that too much. So I might take that slide out. But let's go back to the visible light spectrum for a minute. As most of you guys all know, the colors of the rainbow and the colors that the human eye sees range from an indigo, dark purple, all the way through red. And the reason the color varies is because the wavelength of that light is, the length of the wavelength is changing. So red is a very low spread out light wave versus indigo is a very, very tight sign, very short wavelength. And they range from, the visible light spectrums from 400 to about 700 nanometers. Now, that's the visible light spectrum. Out of the entire light spectrum, our visible light spectrum is very, very small. So there's your gamma rays, your X-rays, your ultraviolet light, then our visible light spectrum, then it gets into the IR spectrum, that stands for infrared. Then we get all the way up into microwaves and radio waves. I always think it's microwaves I can understand can be similar to light waves because they create heat and they heat up our food in a microwave. But it's really interesting to think of radio waves as being similar to light waves, but so far spread out that they're not visible to the human eye. So that's the visible spectrum. Let's look at color temperature. Okay, this is going to be the number one thing that's going to mess you up when you're buying a light bulb is, and I blame the lighting bulb industry for it, 500 Kelvin is a very, very cool light. But what they're going to say on your light bulb package is daylight. But what we perceive better as humans is warm lights, which is a different temperature than the stark, pure daylight. So don't be fooled by the terminology daylight bulb when you're looking at light bulbs. Always look at what the actual color temperature is. Very, very cool temperatures that are going to have a very kind of white, kind of sanitized color to them are going to be closer to the 5,000 Kelvin range. And then a very nice warm incandescent light is going to be closer down to the 2,700 Kelvin range. The happy medium that you can always go with is 35,000. 3,000 to 4,000 fine, but a nice 35,000 color temperature will work like 90% of the time.
I'm sorry, you mean 3,500, right?
Yes, I do.
Okay, just
added
making
an extra
sure.
zero.
Just making sure we're on the same page.
I can't read my right glasses on. I do. 3,500. You are correct. 2,500 is a very warm, incandescent bulb temperature, kind of like a fireplace glow. Gives a very yellow light. And 5,000 Kelvin temperature color is a very stark blue white that's kind of like a hospital, very clean, but not as comforting. Okay, now that I've got my decimal place right, so that's color temperature. Now, Let's look at CRI, the color rendering index. This is a scale that's measured on a scale of 100, so 0 to 100, 100 being as ideal as possible. Different technologies of light bulbs or lamps will produce different CRI values within different visible spectrums. So, for instance, daylight. Trying to simulate daylight, it's a fairly nice, even distribution across the color spectrum. But compare that to a fluorescent light bulb where the color spectrum, visible light spectrum is completely not there. You're getting a lot of green and orange. That's probably #1 reason why people hate fluorescent lights. Incandescent is a very warm light color, so a lot of the orange and the red range of the color of the visible spectrum. Halogen, also very nice quality for CRI, a lot more based towards the warm side. Then with your LEDs, and take these two with a grain of salt, because LED technology is constantly improving and getting better. So I fully expect it to keep on getting better. But again, paying attention to your color temperature. If you have a very cool color temperature LED in the like 5,000 K temperature range, you'll get a very, very blue light. You can find LEDs that are now a lot warmer, and I believe they have even better ones now that are even more similar to incandescent light bulb with that yellow orange glow of like the fireplace. Keep in mind, when we're rating light quality, daylight is the basis of what artificial light is compared to. And that would be yet another reason why daylighting can do so much for your design, and is #1 preferred method for lighting. So at these different color temperatures, the color rendering index will vary. I would encourage you to pay attention when you're working on lighting designs to never have anything less than a CRI of 80, unless you're doing like a warehouse or a garage or a place where people aren't trying to function on a daily work basis. 90, perfectly acceptable. Very nice quality of color light. If you go up to a CRI of 97, this will probably be exclusively used for extremely high-end application, such as a jewelry store case, possibly clothing stores, fairly high-end, but high-end retail or museum quality lighting is the only time I've ever really seen a CRI of 97 be required. CRI of 90, very good. Don't go less than 80. That's my 2 cents there. So let's look at a light fixture. This is a cut sheet for a light fixture. This is a recessed fixture. It's LED because it's tiny. It's a 4-inch square opening. Light fixture cut sheets tend to be multiple pages. This is page 1. So what it's doing is it's telling us the various options on the fixture and what's available, including, let's just go through these. So this is the series, that's the name of the fixture. Aperture is the opening. Installation, new construction, remodel. Sometimes if it was wet listed, it might be here. If you're doing, or underwater fixtures, like if you're doing a pool or a pond or something. If you're doing outside light fixtures, wet listing is pretty mandatory, but it doesn't have to be waterproof, just wet listed. These are some options. So this fixture can come in 120 or 277. This means this can run on a residential power system. 277 would be a 3-phase commercial project. Or you can get it, sometimes they come capable of both. It looks like universal. Okay, this one will come and you can hook it up to either type of system. And that's actually not that unusual. Although, if you're working on a residential project, you really don't want any 277 volt fixtures. But it's possible to put 120 volt fixtures into a commercial project. Okay, it's a downlight. Okay, so then we get into our options, lumens, CRI. There's a variety of lumens you can specify along with your CRI at the different color temperatures. This is all going to be caught up into the bulb that comes in the fixture. Dimmable, voltage, flange, reflector. There's often different types of reflectors based on how much. The reflector is the part that goes behind the bulb and shines down. Like if you want it to be really bright or if you want it to disappear, you could get a specular or a black matte. Okay, so that's page 1, talking about the fixture and all the options. Another page would typically have all your dimensions. So if you're detailing a ceiling assembly or something, or you need to look at your floor to ceiling height, make sure you can fit your fixture in, especially if you got like a duct going by or pipes above. Look at your clearance height. This is only 4 inches high, so it's pretty small. Then this is the page that talks about the performance of the fixture. And this is a typical lighting curve that is saying, this tells you, these are distances, these curved line here's 292, 584. This is the spacing of from the center of the fixture that goes out and what the candela amount is at each distance based on the degree of the fixture. So 30 degree versus 60 degree. So it gives you all of these values. So if you know that you want this light to throw 10 feet, well, actually, let's say 7 feet, that is probably the third curve here. So it's probably around here would be 7 feet. You get this intensity at that surface approximately right there. So at 7 feet, your foot candles hitting a surface would be 46 foot candles, which is pretty high. That's like serious reading level amount. And it also tells me how much energy, watts per square footage, it's using there. So The biggest thing to understand about this is different lights will have different throw shapes. So take a look, see how that's affecting it, and the distance from the center of the fixture to your surface where it's hitting, because this is a down light, so it's a straight up direct lighting fixture. And I'm sorry, I missed this here. This is single unit data. This is multiple units. So if you have lots of fixtures centered, you're going to get multiple coverage overlapping each other versus just a single one. At 7 feet, a single fixture will only get you 30. And there should be a guide on here how far apart to place the fixtures to get that beam diameter. I blew up this picture, so I'm not sure where, but if you're going to look at the multiple data, somewhere there would also be spacing information. So takeaways from looking at a lighting cut fixture is look at the options and pay attention to what CRI and what color temperature you're specifying or your electrical engineer is specifying. Make sure it's wet listed if you need it to. Get your dimensions to make sure it's going to fit. And then have an understanding of what the lumens are at the surface it hits. What are we doing on time? 4 o'clock. Okay. We're getting there. All right. Couple different lamp types. We looked at these briefly when we were, or we looked at the CRI effect of these different lamp types a minute ago. Incandescent light bulbs are being phased out. You're not going to be able to, you can still get them, but they're not as common anymore. And eventually you're not going to be able to find them. Mostly just because they use so much more electricity. And the LED technology has come so far in the last 20 years. Halogen, again, being phased out. Halogens are really nice quality light, but again, they're an energy hog. So they're going to be more and more rare. LEDs, that's where it's at. There you go. And they change frequently because they keep getting better, which is a good thing. But do not be, LEDs will still output heat. They get very, very hot in the housing of the back of the fixture. So it's one thing about lighting is it adds a heating load on your space, especially incandescent or halogen, because they also put out a lot of heat with the light. The LEDs, the light coming out of the fixture is not that great, so it's not adding as much of a heating load, but the fixture itself will get hot at the base of it. And so even though your LED bulb is actually very, very small, it will have a housing around it. And there's usually some sort of fin design that helps the heat get out of the fixture, and it's not disappear. I want to say it's aspirate. I'm not saying the right word. Doesn't matter, but it helps distribute the heat out of the back of the fixture. Fluorescent lights or bulbs, still very common, especially more on the industrial end these days, but you're starting to see more and more LEDs replace fluorescent fixtures. Okay, quick note about low voltage lighting. Almost all exterior lighting is going to be low voltage. And low voltage lighting requires a step down transformer to step down the 1 volt power that's coming into our buildings, or 277. and steps it down to 12 volts. The advantage is the amps are so much lower, it's not nearly as dangerous. You can't electrocute yourself with 12 amps on low voltage wire. You can kill yourself with line voltage if you wanted to. Shouldn't say that. It's a lot more, line voltage is a lot more dangerous. Low voltage is a lot less dangerous. It's also much easier to run the wire. The wire's a lot more flexible, and it doesn't need to be in conduit the same way in commercial projects. But you always need to have a transformer, and usually there's a limit on how far the transformer can be from the actual fixtures. You can often use one transformer for multiple fixtures. You just have to make sure it's sized properly to carry the load. So that's low voltage lighting. Okay, before I do the last slide, which is sort of my leave you inspired on how to approach interior lighting design, are there any technical questions on electricity or lighting? I'm not seeing any hands. I'm seeing a few shaking heads. Okay, then what I'd like to leave you with as future architects, just like daylighting is can enhance your design in your project, and I encourage you to use it as a readily available resource. Don't discount artificial lighting in projects either. They can have an equally great impact. After all, we're not always going to be able to rely on daylighting. So, a 5-step approach for artificial lighting is remember that we're attracted to light. So use that concept of phototropism to choreograph how people move through your space. If you want someone's attention to be attracted somewhere, or you want to draw people down a hallway, or if you don't want them to go somewhere, use your artificial lighting to help control how you want people to move throughout the building or the room or the design or even an exterior space. So that's like that's the design aspect. Well, I shouldn't say that. That's like the big picture, pull you here, grab your attention. Then on top of that, you want to make sure you also have your ambient lighting to be of a sufficient level that people are comfortable. Keep in mind that this is what you can rely on with a good daylighting scheme during the day, and you shouldn't need a lot of ambient light during the day unless you're doing a room with no windows, like dark room or a theater or something like that. Keep in mind, you want to make sure that your ambient lighting design can adapt at different periods of the day should you need it. Then your pop and your wow is your accent. And use that lightly and sparingly when you want to attract someone's attention to a certain feature or a thing, like a statue or a painting, something that you want focus on. And then this is something I learned, and actually all of these are things I learned from working with lighting designers. And this one is not, the number 4 is not quite as obvious, but keep in mind your thresholds. And when you move from a space to another space, and how can you use lighting to either enhance that or downplay it? Are these spaces supposed to feel connected, or is there supposed to be a sense of transition when you move from one to the other. So that's something not an awful lot of architects think about, but think about how you enter a building and what the lighting level is on the outside and what it's like when you come in the door. Or if you're moving from a great room to like a study in a residence, you know, is that going to be more of a quiet feel, or where the fireplace is, versus the family room where there's a lot of activity and you've got a lot of motion going on? You know, use your light levels or your lighting fixtures and how you place them to create that, enhance the difference of the space. And then functionality at the very end of the day is, don't forget your task lighting, where you're going to sit or where people sit and where you need to be able to see well. Kitchen countertops, desks, classroom lighting designs, a lot of it's all based on what are the lumen levels where it hits the desk surface. Libraries, they care very much about what those light levels are at the bottom of the stacks. Are they getting enough light down to look at the books at the very bottom of the stacks? That's a combination of ambient and task lighting. But and many of these things can be combined together. Like your choreography can be combined with your thresholds and how you change the sense of the feel from one space to another space. Or your choreography can be combined with your accent lighting and drawing you down a space to focus on a painting at the end of the wall, or turning a corner, or a statue, or a more important space in the building. So if you're going to take anything away, well, there's many things I want you to take away from this class, but in terms of electricity and lighting, I hope that you'll hold on to this slide and take it with you throughout your practice and use it to enhance your projects, and use it to make it better, because I know you guys can do that. So again, a lot of I've been very fortunate over 20, 30 years to have worked with some really good lighting designers. And not all projects get to have lighting designers, but encourage your electrical engineers, who are often the people who are the ones that are going to end up specifying your fixtures. But don't let them just do their job. Make sure that you're actively involved in it and have input and use it creatively. Okay. So that's it for today. To reiterate, I know a few people popped in late. Friday is optional. I guess I'm going to call it like open classroom, open house, office hours. If you have questions about anything and you want to log in and have a chat, or questions about assignments, I will be here on our meeting classroom site on Friday, but it is optional. You do not have to attend. So that's it. Have a great week. I hope all your studios are going well. Almost to the end of the semester. It's, oh, I can't believe like tomorrow's April.
Yeah.
Is it tomorrow or the next day?
Like quick and slow.
Yeah. That's the same thing for life. It goes by fast and then very slow on some days. So I'm going to stop the video now. I'm here. There's a couple of people had a couple questions. So hang out, and I will see some of you on Friday. If not, everyone have a great weekend. And we've got like 3 lectures left. One more assignment after this. And I'm not going to give you an assignment on this one because I know it's the end of the semester and you don't want to do it anyway. Okay, guys.
Thank you.
Thank you.
You're welcome.
Okay, I have a question on,
Yes.
let me share my screen.
Okay, let me turn mine off and make sure that you have and share. How do I do that?
Okay, I think I'm already sharing.
Yep,
Am I?
there you
Yeah,
go.
okay. I just want a little more explanation on the PV watt system information page.
Okay,
I'm just a bit confused on that. I don't know if it's this the PV watt calculator and how we start to, oops. What happened here?
I think you have to put in, oh, you have a site. Okay, go. There you go.
If this
Okay,
is
this
the
page.
information.
This is the
Oh,
information page, yes.
okay, and I don't know if we need to, I don't know if we need to print this as well with this information.
That would be good too. Yes, that would be
Okay.
helpful.
And is that also the production calculation page?
Yes,
Oh, it is.
yes. Okay. So the information page is where you put in all the data, and production is what your site is going to produce. Yes.
Oh, okay, okay. That's all I had. Thank you.
Okay. Great.
Okay, have a nice day.
Thank you for asking that. I'll try and make that more clear next time.
Okay, thank you.
Okay. Have a great night.
Bye.
Can you hear me?
Hi. Yes, I can hear you.
You know what? I just got this laptop, so I don't have to do Ring Central on my phone.